thinking about integrals as helping us figure out the mass when we're given a total density. Excuse me, when we're given a density function, say in grams per square centimeter. We want to be able to integrate that to find the total mass. And the main thing I want to do here to start with today is focus on the concept of why doing the iterated integrals gives you the right answer. And I want to focus on it intuitively. I don't want to bother talking about Riemann sums and limits of Riemann sums. That's in the book, and it's definitely worth doing, and it's definitely worth having a few homework problems where you are dealing with Riemann sums. But I don't typically test you on Riemann sums. It's not something that I like to spend a ton of time on. It is important. I don't mean to denigrate its importance. But to me, it's kind of boring compared to the rest of the subject. So I'd rather be doing the integrals visually, intuitively, and computationally in the ordinary way. So recall back in Calculus 2, when you created solids of revolution, you should recall that you could find the volumes of those solids through integration. Integration of a function of one variable. And the overall idea can be described in general like this. You can imagine you've got some sort of blob, maybe it's like a loaf of bread or something. It's three-dimensional. You've got to imagine that with some perspective there. And you've got an axis. Now this is not a solid of revolution. It's a more general kind of thing. You've got some axis, and you're somehow able to measure what's called the cross-sectional area of this loaf of bread. Imagine taking a knife. Your hand is a knife, and you're going to cut this loaf of bread perpendicular to the x-axis to create a slice. The slice, when you do volumes of revolution, is either circular or washer, where you've got a circle and you've got a part missing in the middle. Think of that as a washer, like with you use a screw. You're screwing something in, you need a washer in there. But this thing, this cross-sectional thing, doesn't have to be a circle or a washer. It's just some general object that's got area that depends on x, a of x. And ultimately, you integrate that function. You integrate a of x from a to b to get the volume of the solid. Intuitively, if you're thinking in terms of differentials, these infinitesimal things here, if you imagine this having width, so to speak, dx at this number x, then the infinitesimal volume, dv, can be thought of as a of x times dx. Again, this is just intuitive, non-rigorous math. We're imagining the infinitesimal volume of this thing as being its cross-sectional area, the area that I'm shading here, times this infinitesimal width, a of x times dx. And then to find the total volume, v sub tot, you add up the infinitesimal volumes, which effectively means you integrate a of x from a to b. That same idea can apply to understanding why you do double integrals as iterated integrals. Why you have an inner integral and an outer one. I think I'll do it behind the screen here. The positive x-axis come out of the board, the positive y-axis go to the right, and the positive z-axis go up here. If we've got the graph of some function of two variables here over some rectangle, say, let's see if I can draw this right. Maybe I should put this more like this here. So we've got some rectangle here that's our domain. This doesn't look real good. Something about like this. Got to draw with a little bit of perspective there. So this is the graph of our function, z equals f of xy. Down here, this rectangle that you got to think about what perspective is going into the board in the XY plane here. That's your domain, your region of integration. Let's say x goes from A to B and y goes from C to D. You can slice this with vertical planes, either perpendicular to the x-axis, parallel to the yz plane, or perpendicular to the y-axis, parallel to the xz plane. If we slice it perpendicular to the x-axis, say you slice it right here at this value of x, you're going to get a cross-sectional area, just like I talked about over there. Something about like this. That has area A of x. A little hard to see there, isn't it? Something about like this. That area can be found with a one-variable integral. Integrate this curve up here, that's a function of one variable, just a function of y, right? Y goes left to right here. For that fixed value of x, think of this as a fixed value of x, where that's a variable x. This is a fixed value of x. For that fixed value of x, this curve up here is the graph of a function of y, this function of y where x is fixed. It's a function of y integrated with respect to y, where y goes from C to D. See the C back here? C back there. Y goes from C to D. That's going to give you the area under that curve. And that's the same as the cross-sectional area function. That's A of x. Same idea as back here. Integrate that function from A to B to find the volume. So the total volume under the graph is going to be the integral of A of x with respect to x, where x goes from A to B. But what is A of x? A of x is that integral. Therefore, we can write this as an iterated double integral. Where you integrate with respect to y on the inside and with respect to x on the outside. Again, why do I call it an iterated integral? What's the reason I say it's iterated? There's an inner integral and an outer one. The inner integral gives you the A of x. The outer integral integrates A of x to find the total volume in the same way that we talked about with the loaf of bread over this. But we can also slice it perpendicular to the y-axis to get a graph like that, and a cross-sectional area over here. Cross-sectional area, oh boy, about like this. And you could call the area of that A of y. See where it is here? Take an extra bowl. Call the area of that one A of y. That depends on what y is. It can be found via an integral as well. Integrate f of xy again, but now you're treating the y as a constant. X is a variable. That integrates the x out, leaving you with something that depends on y. Ultimately, the volume can be found by integrating A of y from C to D. But A of y, again, is this integral. So once again, we write it as an iterated integral. This is by no means a proof. These are all intuitive derivations that make good intuitive sense and are an intuitive reason why it doesn't matter what order you do the integrals in. Okay? What about if we were going to integrate over a region that's not a rectangle? Closed and bounded disk. So less than or equal to. Pretend this is a circle. There's your circle of radius 5 centered at the origin. The disk includes the circle and also includes all the points inside. That's the domain we're considering next. And again, don't forget what I said the other day. These integrals, though you can interpret them as volumes, also do give you the total mass of the thin plate. Right? Talked about that too. But now we're just thinking about the geometry of it. Now worrying about the mass interpretation here. What should we do now? What's going to happen? Let me try to draw. Actually, if I draw an accurate picture of this function, the same function we were dealing with already, I would probably want to try to make it more like Mathematica makes the graphs. Make the positive x-axis go to the right, the positive y-axis go into the board, and the positive z-axis go this way. The graph is a little easier to make and orient them this way. I'll remind you of that. These are three-dimensional plot. But again, we want to restrict this to just over the disk. Actually, here we can look at everything at once. This was the code that does everything at once, including thinking about the Lagrange multipliers. So focus on the graph. Oh, I don't know why it's. Wow. Focus on the graph to the right there. That's what I'm going to try to draw by hand. Something through here. Try is the key word there. Is that good enough? Something like that. That's the density function. That's not the disk itself. The disk itself is in the xy plane, the thin sheet of metal. This is the graph of the density function. The volume of the solid formed by taking this graph and projecting it down into the xy plane to create a solid, its volume will equal the mass of the disk. And it is the thing we're after here, the double integral. So if I project this down into the xy plane, this is supposed to be d2 here. X. You know, I used to draw a lot, but not so much as I've gotten older here. I'm not as good at drawing. We can still do the slicing. Let's slice it perpendicular to the x-axis, parallel to the yz plane. Let's pick a particular value of x right about there, say. What is the cross-section going to look like? Something, I don't know. Actually, it's probably simple. It's probably a parabola. Isn't this quadratic in x? Yeah, I think if this was a quadratic in x, it's going to look like part of a parabola. Something like that is going to be the cross-sectional region here, the cross-section itself. Its area we can call A of x. We want to integrate that area function to get the volume. Integrate it from -5 to 5. X goes from -5 to 5. Note that since the solid sort of gets pinched here when you get close to 5 or -5, that A of x, it appears, has to go to 0 as x approaches -5 or 5. You have smaller slices. Well, they're small in this direction. They're still fairly high over there, at least. Anyway, you've got to integrate this function to get the volume. And you can think of this as a dv initially, if you like. Imagine it as a product. It's not literally that. Imagine it as being the cross-sectional area, a of x times the infinitesimal width of this thing. Over here. Imagine that as being infinitesimally small width to this thing. And that is a multiplication to give you the infinitesimally small volume. Imagine the integral is telling you to add up those volumes to get the total volume. That's an intuitive reason why this integral gives you the total volume. But what is a of x? A of x itself can be found with an integral. A of x is an area. This area here, the area under the graph of a function of y, right? Y is going in that direction. I've got to integrate some function with respect to y to get a of x. What function? Well, it's the same function, f of xy, although you think of the x as being fixed when you are doing this inner integral. Effectively, that tells you you're thinking about this particular slice right there. What are the limits of integration? That's the trickiest part. Got a guess? Based on the pictures? Maybe this is helpful. Think of that as a particular x. Draw a line there. Well, the problem is, for a fixed x, y doesn't go between -5 and 5. It goes between the second coordinate of that point and the second coordinate of this point. The equation of the circle is x squared plus y squared equals 25. What are these second coordinates going to be in terms of x?
Square root of 25 minus x squared.
Yep, plus or minus square root of 25 minus x squared. Those are the two values of y that correspond to that value of x on the circle, those 2 points, and those are going to be your limits of integration. Your limits of integration are going to depend on x. Negative square root of 25 minus x squared to positive square root of 25 minus x squared. That inner integral gets rid of the y, so to speak. It integrates the y out, leaving you with a function of x that you can now integrate with respect to x. I'm not saying the integral is going to be easy. Where's our function here? There it is. An antiderivative of that function, do the inner integral with respect to y, is not going to be too hard. The first step's not too hard. Let's just do a pure indefinite integral here. That's fairly easy, right? Do that. Treat the x as constant. Integrate this with respect to y, get 250y minus 5x squared, oh, excuse me, minus 10xy. Treat the x as constant. Plus x cubed y. Plus, okay, 3/2 y squared, yep. 1/3 xy cubed, yep. So that's not too bad, but then when you plug in those limits of integration, that's when it starts to get kind of nasty looking. If I do this as a definite integral with those square roots, this. I've got to plug in the top one. Into what? This upper limit of integration is going to get plugged in here in place of y, right? We integrated with respect to y. You'll get a square root there, a square root there, you'll get a square root there. You won't get a square root there, but you are going to get a square root there because you'll have something to the 3. 3/2 power. So it's not going to be pleasant looking. And you can count on me not making your exam question that difficult. Well, you know, that's not so difficult to calculate. Doing the integral of that's going to be more difficult. Let's simplify it first. That's the a of x function. If you're going to integrate that by hand, it would be pretty nasty. You have to do a trig substitution. X equals 5 sine theta. Then dx would be 5 cos theta d theta. You'd have to deal with these here. Maybe split it up into 3 separate intervals. I think integrating just this part ended up being similar to a problem that we did earlier in the semester that ended up like taking the entire board. It was pretty nasty. Remember that fanciest trick during integrals that I've ever seen to integrate secant? Multiplying by secant theta plus tangent theta divided by secant theta plus tangent theta was a trick. It was pretty nasty. Okay, this would not be something you'd want to have on the test. So you can expect easier problems on the test, but it is doable, technically speaking. Integrate that from -5 to 5. I'll just go ahead and copy and paste this in here. It's doable. There's the answer. Is the average value of this density function over the disk still 250, like it was over the square? Remember that? Over the square, the average density was 250 grams per square centimeter. Is that true over this disk? It's going to be true if you take the average value, pretending it's 250, and multiply it times the volume, or the area of the disk. Pi r squared, 25 pi. It's the same, yeah. 250 is still going to be the average density in grams per square centimeter over this disk centered at the origin. Again, if I centered it somewhere else, the symmetry would break down and probably the density would not be the value of the density at the center of the disk. Fortunate here by the symmetry that this seems to be working out nicely in terms of the average density. You can do it the other way around. Evidently, we can get an a of y as well, and by symmetry, it's really going to have the same formula. A of y is going to be the integral from negative, this was an a of x here, yeah, sure. Negative square root of 25 minus y squared to positive square root of 25 minus y squared. There's symmetry in the domain here. When you think of it this way, when you think of this disk as being essentially between the graphs of two functions of x, plus square root of 25 minus x squared and minus square root of 25 minus x squared, in the book they call that vertically simple. It's vertically simple. A vertically simple description of this region. Vertically simple. When you do this, when you think of the inner integral as giving you the cross-sectional area as a function of y, so you're slicing the solid with slices that are perpendicular to the y-axis to get cross-sections that look like this. That effectively is thinking of this same region as being what's called horizontally simple. As being the region between the graphs of two functions of y, not x, y. When you think about those as functions of y, you effectively have to turn your head sideways and actually, ideally, even look in a mirror. So get a mirror out, turn your head sideways like this, and look at the graph in the mirror. Then it'll look like an ordinary graph. The positive y-axis will be to your right when you're looking at it that way. These are two functions of y, and when you think of it that way, you think of it as horizontally simple. That's when the inner integral is like this. And the outer one is to integrate that function from negative 5 to 5. Meaning, you ultimately, when you think of it as an iterated integral, you're thinking of it like this. The inner integral is with respect to x, giving you a function of y after you do the inner integral, and then you integrate that with respect to y. And again, by symmetry, the calculations would be the exact same thing here. But there are definitely situations where doing it this way might be easier than doing it that way. You'll encounter some of your completion homework. Where doing it one way is easier than the other. So you do want to have the flexibility to do it either way. I was going to say something else. Oh yeah. With regard to this vertically simple versus horizontally simple, there are some regions where it's definitely better to think of the region one way versus the other, and maybe even, in a sense, impossible to think of the region the other way unless you break it into pieces. For example, if you've got a region that looks like that, it's the region between the graphs of two functions of x as x goes from a to b. You've got an upper function and a lower function. You call this y equals g of x down here, and this one y equals h of x. This is your domain of integration, right? We're still talking about doing a double integral here. So in terms of the graph of the function, the graph would be in front of the board and sideways. You're integrating over this region. This region is vertically simple, but not horizontally simple. Vertically simple. It's the region between two functions of x. And for your inner integral, you're going to want to integrate between those two functions of x to get a function of x here. Your cross sections are going to be perpendicular to the x-axis. The inner integral is going to integrate the y out so that what's left depends on x. For fixed x, y goes between g of x and h of x. Integrating that function then gives you the total volume. Integrate that function from a to b. And you write the double integral like this. And again, I'm using parentheses just to consistently emphasize the concept of what's going on here. You do not have to include parentheses when you do your work. Continuing to the left, a horizontally simple region might be something like this, and this would be horizontally simple but not vertically simple. Horizontally simple. Y goes between two numbers c and d, and for each value of y between c and d, x goes between two things that depend on y. You call this graph x equals m of y. In this graph, maybe you call x equals n of y. I'm purposely drawing those kind of sideways. It'd be a problem though if you get your mirror out here, then, well, you know, an m's kind of symmetric. Well, I guess these are both kind of symmetric, but then it would look goofy. Okay. That's horizontally simple. The inner integral would give you a function of y. You integrate with respect to x to get that. Between these two functions of y, m of y and n of y. And then the volume, once again, would be to integrate that function from c to d. Okay, so I'm giving you some conceptual machinery to try to understand what's going on here, and hopefully also help you make the distinction between horizontally and vertically simple. If the region is vertically simple, you're going to want to do it this way unless this integral is impossible to do by hand. In which case, you still can't think of this as horizontally simple, but you can maybe break it up into pieces that are. That would be a pain, though. Let's see. Yeah, it's a pain. Maybe one region. It's also easy to not quite tell what's the best one to choose here. Maybe one region that looks about like that. That's horizontally simple this way. I think that works. Well, it's tricky, okay? I guess we could cut it like that there, etc. Okay, you can break it up into a bunch of pieces that are horizontally simple, but that's going to be a lot more work. You can't do this on a really in the ordinary way, like if this antiderivative is impossible to find, then you have to do it in pieces. Question?
So if like h of x and g of x ever intersected, would it then not be vertically simple or horizontally simple?
You'd have to break it into pieces. If they crossed, think of it as two pieces that are, in this case, vertically simple. And then the roles of h of x and g of x we can switch around, which is the upper limit of integration and which is the lower on each piece. Yeah, you'd have to do that. All right, with the remaining time, let's focus on going back to optimization. Thinking about optimization of functions of three variables. Ultimately, what you're going to see on the take-home exam, you're going to see a function whose domain is the three-dimensional space R3 and whose codomain is the real numbers, like this function here. All I did was I took the other function and added a z-squared in there. And we want to optimize this ultimately over a cylinder. The domain is going to be a cylinder. In fact, it's going to be the disk of radius 5 centered at the origin, translated up and down so that z itself also goes between -5 and 5. That's what the cylinder I'm going to pick, in this example at least. We're not going to get quite to finding the global max and global min today, for sure on Wednesday. Today I'm going to focus on these local maxes and local mins and saddle points. Here are the first derivatives, here are the critical points in 3 dimensions. Here was the contour map, we saw this before. Got the critical points in there. We want to try to classify those critical points as local maxes, local mins, or saddle points, some sort of higher dimensional saddle point that you, it's hard to understand how to visualize it at first. And what I said at the end of class the other day was that you can do sort of a second derivative test in this context. But it does get more complicated, as you might expect. Two main matrices that we're going to deal with today and in coming days, including after the exam, are called Jacobian matrices and Hessian matrices. Jacobian matrices are going to be matrices whose entries are first derivatives of what's called a mapping. As an example of a mapping, the conversion equations from polar coordinates to rectangular coordinates. Those two equations combined can be thought of as defining something called a mapping from the plane to itself. That's not the kind of matrix I'm going to talk about today. Instead, I'm going to talk about something called a Hessian matrix. It's a matrix whose entries are second derivatives. In the case where you've got a function of two variables, f of x, y, it's fxx, fxy, fyx, fyy. We already talked about that, in fact. We talked about how the discriminant, D, is the same as the determinant of that matrix. That matrix is called the Hessian matrix for that kind of situation. In 3 dimensions, for a function f of x, y, z, the Hessian matrix is going to be 3 by 3. The first row is going to consist of all second derivatives, second partials of f, whose first differentiation is done with respect to x, and then whose second derivative is done with respect to either x, y, or z. There's the first row of this Hessian matrix. Second row, y is going to go in the first spot. fyx, fyy, fyz. And the third row, z will go in the first spot. fzx, fzy, fzz. Everything here is a function. Entries in this matrix are functions. The matrix itself is a function of x, y, and z. By Clause's theorem, when your function is nice, which we always pretty much deal with nice functions here, these mixed partials are the same. Those two are the same. These two are the same. And this one is the same as this one. So actually, you don't have to calculate 9 distinct partial derivatives. It's enough to calculate 6 distinct ones. There's some symmetry in the matrix. It's in fact called a symmetric matrix. And it turns out symmetric matrices like this always have real eigenvalues, and we're going to calculate those things called eigenvalues to understand and to classify these critical points. I'm not going to say what eigenvalues are. Okay, that's in a linear algebra class. You can calculate eigenvalues for any square matrix like this, like a 3 by 3 matrix. If you're interested in these eigenvalues and how they are calculated, go ahead and take linear algebra, and even diffie-q too. We'll talk about how to calculate eigenvalues in differential equations as well. But let's just get these second derivatives. Okay, let's do some copy and paste action here. I need six distinct ones. fxx, fxy, fxz, fyx, which we've already done with fxy, fyy is new, fyz is new, and finally fzz is the only new one left. Oh, I got the cat block off. Go. These are the distinct second order partial derivatives. Let's create the Hessian matrix now. Let's go ahead and call it just Hess of x, y, z. In general, it will also depend on z, but we don't have any z's in these second partials, so we won't see any z's in the matrix. You can get the matrix into Mathematica with the basic math assistant here. Here, there's a matrix button right there. Click right there, click this button, there's your matrix. It's only 2 by 2 at the moment. To add a row on a PC keyboard, you do Control Return. Return starts with R, just like row starts with R. And if you want to add a column, do a Control Comma. Comma starts with C, just like column starts with C. On a Mac, instead of the Control key, use the Command key. Command return command comma. All right, let's go ahead and put these functions in here. 6x is fxx. 2y is fxy. 0 is fxz. Let's see. By symmetry, fyx is 2y. fyy, that's the 2x here, right? That's 2x. Yeah. Should be 2x here. Fyz, that's the 0 there. By symmetry, we get 0 here, and then 2. I've done this right. I'm not sure why these are green and these are blue. Why are they all green? Hope this works. Now they turn green. What do you want to do with these? You want to plug the critical points into them. The first and second coordinates of the critical points. Let me copy and paste these down here so we see them. I could try with map, but I'd have to deal with the fact that those critical points are three-dimensional. Well, maybe if I use curly braces here, maybe this would work. Let's try using that map function I showed you before. Apply the Hess function across these critical points. Let's see if this works. I think it did. See those as matrices. Oh, that doesn't look good. Okay, I'm not sure why it's splitting these things apart like this. But let's not worry about using that. Okay, let's figure out the Hessian matrix. Hess of negative 0.493, comma 3.045, comma 0. Look at it in matrix form. That matrix, just like with the second derivative test for functions of two variables, when you calculate the discriminant d, you only plug in the critical points. Same thing here. You only plug the critical points into the Hessian matrix. There it is. What are its eigenvalues? Just do this. Eigenvalues of this. I told you what would happen last Friday. I said you could get all positive eigenvalues, you could get all negative ones, you could get mixtures of positives and the negatives. They have to be real eigenvalues actually, because symmetric matrices only have a real number of eigenvalues, no imaginary or complex number of eigenvalues. That's a fact from linear algebra. Again, I'm not telling you how to compute the eigenvalues, we're just trusting that Mathematica can do it. And you're trusting me when I say that if the eigenvalues are all positive, that means the point is a local min. It's kind of like somehow, in some way you can't visualize, the graph is concave up in three directions. Oh, okay, maybe we shouldn't go there. There's a mixture. There's a mixture of positives and negatives, so there's some sort of higher dimensional saddle point. What about this one where these signs change? That's also a higher dimensional saddle point. What about the other two? That one's all positive. That's a local min. What about this one? That one's a mixture, so that's a saddle point. So one of the points is a local min, and the other three are saddle points. Let's see if we can end class today by showing you a kind of cool visualization to see why this one is the local min. We won't bother seeing why the other ones are saddle points intuitively. Let's see, I need to find the value of the function at that local min. What's f of 10.94, comma 3.124, comma 2? Oops, no, sorry, those are the eigenvalues. What's f of 1.758, comma negative 0.853, comma 0? 236.573. Let me copy and paste this and make an animation with manipulate where I just plot one level surface, not a bunch of them. I'll get rid of this contours arrow 20. I'll make this equals C, where C will be my animation parameter. Starting, say, at 230 and going up to 240. See, I'm going to the output. Output value is close to that minimum. C starting at 230 and going up to 240. Probably have to do a performance goal here. Performance goal. Arrow quality. Okay, so again, we're only seeing one level surface here. For one value of C, C equals 230. Watch what happens now as C increases past the value of the output at the critical point, the local min, which was 236 something. All of a sudden, look at that. Isn't that cool? We get as C increases, we get this ellipsoid kind of thing around this critical point where the local min was, when there was nothing there before. All of a sudden, this ellipsoid type of shape gets generated. I'll let you think about why that implies this is a local min as C increases. Okay, see you in class on Wednesday.